Hey guys, this is Miss Martin, and I am going to be reviewing with you isotopes and isotopic notation. So what are isotopes? An isotope is like a different version of the same element. We know it's the same element because it has the same number of protons. So remember, the number of protons determines which element you are. If you are hydrogen, you have one proton. And if I add a proton, then you're no longer hydrogen, you're helium, and so on and so forth. So changing the number of protons changes the element. An isotope is sort of like a different species of the same element in that it has the same number of protons, but it has a different number of neutrons. Now, why do we care about the neutrons? Neutrons help keep the atom and especially the nucleus stable. And if you've heard of isotopes that are maybe radioactive, then you're looking at an isotope of an element that is currently unstable. So neutrons just really help out with keeping everything together. So, an isotope. Here are two pictures of different elephants. They're both elephants, but one is an Asian elephant and one is an African elephant. So they're both elephants, but they're different species. In the same way, you can have an atom that's pretty close to being the same, like carbon here, but if it's an isotope of carbon, then it's slightly different. So this here is carbon-14. We use carbon-14 to date anything that used to be alive. We use it to see how long ago it lived and a few other pieces of information about that particular organism. So carbon-14 is just like regular carbon. It has 6 protons, and we write that down here. We write the atomic number on the bottom for carbon. But unlike regular carbon that you see on the periodic table, carbon-14 does not have 6 neutrons. Instead, it has 8. And so those 8 neutrons just make carbon-14 a little bit unstable. Because it has the 6 protons, again, it's still just carbon. But adding those 2 extra neutrons turns carbon-12, the carbon we're familiar with, into carbon-14. Now there's 2 different ways to write this. You can write C, the element symbol for carbon, dash 14, or you can show sort of the isotopic notation here on the left. Isotopic notation is simply the element symbol, and then at the top you have the atomic mass rounded to be the mass number of that particular isotope. So carbon-14 here, I got the 14 because it's 6 protons plus 8 neutrons. So it's the same thing we've been doing for mass this whole time. It's the protons plus the neutrons. But normally, carbon's mass we talked about so far, it would be 12, right? If you look on your periodic table, then you will see 12.01 as the atomic mass of carbon. You would round that to 12. But those 2 extra neutrons give it a little bit of extra mass, and so it goes to be carbon-14. So you write the mass up top, and you write the number of protons or the atomic number down here at the bottom. So it ends up looking a lot like the periodic table tile, just flipped. And then you replace that old mass with the new mass. All right, so we're going to observe a couple differences real quick between isotopes. Where we are, if this vet lab works. There we go. Okay, so in this vet lab that we all did together, we saw a couple of different things. Number 1, we saw that adding a neutron does a few different things. So we see how it's still hydrogen. So adding neutrons, you are not able to change the element. The only way you can change an element is, again, by adding a proton. So see how there's one more red dot here than there was before. That is the proton, and that is the only way I can possibly change my element. So by adding a neutron, I'm doing a couple other things. Number 1, I'm changing the mass number. So I'm adding mass to this. Number 2, I am making this one is unstable. See how it's shaking back and forth? So that atom is unstable. And, okay, A couple other things. The abundance of nature just refers to how common is this found. So the hydrogen on the periodic table has 1 proton, 1 electron, and 0 neutrons. We see that information up here. And it makes up 99.9% of all the types of hydrogen in the entire universe. But if I add another neutron, and I get what you would think is a more balanced molecule, right? Or a more balanced atom. You have 1 proton, 1 neutron, and 1 electron, so 1, 1, 1. But even though this maybe makes more sense to us, this hydrogen only occurs 0.01% of all the time. So not even 0.1%, not even 1%, but 0.01% of all of the hydrogens floating around, all the things that just have 1 proton. This is how many of them look like this. So it's pretty rare. And so how this hydrogen 1, got to be the hydrogen on the periodic table is because it's the most common one. So we put the most common isotope on the periodic table, and that's why whenever we did the atomic math together, you might have seen that there's a few elements that have a different number of neutrons than protons, but not all of them. Like lithium here. Lithium-7 is the normal one, 92.4% of all lithiums look like this. Lithium has 3 protons and 4 neutrons, so a different number, an atomic mass of 7. So what if I even that out? Well, it becomes unstable. Sorry, what if I even it out this way? Okay, this one's still stable, but even though there are 3 protons and 3 neutrons now, it still only makes up 7.5% of all of the lithium atoms in the universe. It's a pretty small amount. So just to recap, we're seeing 3 things change when we make an isotope. The number of neutrons is what determines if it's an isotope. Changing the number of neutrons changes just the mass number, not the atomic mass. Sorry, not the atomic number, just the atomic mass and the mass number. It also changes if it's stable or unstable. And then finally, it changes the abundance in nature. And then up here, we saw it written in isotopic notation. So that 6 goes here, 3 goes on the bottom. This is the number of protons that 3 is, and that never changes. If we're talking about lithium, then it's always going to have that 3 on the bottom. But as I go, then we see just the top number is changing. So it goes 8, 9, 10, and 11. So this is our mass, and to find the number of neutrons total, instead of just looking over here, I can take 11 minus 3 and end up with 8. So there's 8 neutrons.